We know that water, right, has a boiling point, and it's 100 degrees Celsius or 212 degrees Fahrenheit. We know that water has a freezing point, which is 0 degrees Celsius or 32 degrees Fahrenheit. Well, we use those numbers, but they're not exactly accurate. I don't know if you've ever maybe baked a cake or muffins or something like that, and if you look, they'll have high altitude directions on there. Or when you're boiling noodles, sometimes they'll have high altitude directions on there. So if you were to go up to Flagstaff, what happens is water doesn't boil at 100 degrees Celsius up in Flagstaff. It boils at a slightly cooler temperature. So that means because you're higher up in the atmosphere and there's less atmospheric pressure, it causes things to be able to boil at lower temperatures. So now when you put in your macaroni and cheese and it tells you to boil the water with your macaroni and cheese in there for 8 minutes, well, you have to boil it maybe for 9 minutes because it's actually boiling at a cooler temperature. So pressure and temperature together have an impact on the boiling point and melting point of different substances. So this one here is just a generic graph, and they'll be more specific with values when you're looking at certain substances. But in this case, you see this whole section over here listed as a solid, listed as a liquid, and listed as a gas. So what that's telling you is no matter what your pressure is, if there was values in here, that if your temperature is cool enough that you would be in this solid state. So if you were at this temperature and at this atmospheric pressure, you would be in this solid section, so it would be a solid. Well, if it got warmer, let's say all the way out to here, if it got to this temperature, well, if you were at this temperature and this pressure, you would still be a solid, right? And at this temperature and this pressure, you'd still be a solid. But if you were right here at this pressure, well, now all of a sudden, it's going to be a liquid instead of a solid. YouTube boiling water in low pressure, or boiling water in a vacuum, and you'll see little videos of where people will create a vacuum and you'll have water at room temperature, and all of a sudden it'll start boiling, because even though it's at room temperature, which is pretty, it's kind of cool to see. It's unique. So on this graph, right, it's relating the pressures and temperatures. Now, you see that there's these lines in here labeled melting and freezing, right? We talked about those phase changes in a previous assignment. If a solid goes to a liquid, it melts. If a liquid goes to a solid, it's freezing. So when you pass this boundary, whether you pass it at this pressure and temperature or this pressure and temperature, your object is going to melt. Or if you're way over here to the right, and let's say you're at this temperature and this pressure, now if you heat up that liquid, when you get to this point, so this temperature, whatever that mark is, that would be the boiling point. That's when your liquid would start to boil and vaporize into a gas. Right? Same thing with now all of a sudden, if you started cooling a gas, right? You're in a gas and you're cooling and you're cooling and you're cooling and you're cooling because you're at this atmospheric pressure. When you reach this point, now all of a sudden, you're at the point where it's going to condense. That gas is going to start condensing back into a liquid. And so that's how you use this graph, and you'll see on the worksheet it's going to ask you specific questions. So here's one with different values. This one over here is kilopascals for pressure. That's a unit of measurement for pressure. You're also going to see a unit of measurement for pressure of atmospheres. So under normal conditions at sea level on Earth, at a standard temperature of I believe it's 0 degrees Celsius, then the pressure is 1 atm, 1 atmospheres. And temperature, we usually do deal with degrees Celsius. So you can see here, like let's say we're looking at 0 for our temperature and 101 for our pressure in kilopascals. We're at this point where we're between an ice, right, a solid and a liquid. So if you were to heat up the substance, well, you'd move over here on the graph and you'd turn into a water. Or if you would cool it, right, then it would turn into ice. And so you can look and see at certain temperatures and at certain pressures, like what's the boiling point. Let's say you're at 22,089 kilopascals and you're at a temperature of 374 degrees Celsius. Well, this here, because it's the boundary between the water and the gas, that's going to be your boiling point when it's going to start to boil. Or if you're at, this 0 degrees and 101, well, this right here at 0 degrees, well, that's your freezing point. If you're at a pressure of 101 kilopascals, which is roughly 1 atm, then your freezing point, right, is 0 degrees Celsius, and that's what it is for water. Or if you're at 1 atm or 101 kilopascals and 100 degrees Celsius, well, now you're at the boiling point because you would transition into that water vapor part. Now, like I said, there was a video out there that said you could take liquid water and have it evaporate if you were to put it under low pressure. So now all of a sudden you have water at atmospheric pressure at this temperature. Well, instead of heating it up or cooling it, you instead decrease the pressure, and so the pressures are getting smaller and smaller and smaller. You can cause it to evaporate, right, or boil. So all of a sudden at this lower pressure, you have a different boiling point. Now, if you relate that to our nuclear reactor, what happens is they go under high pressures, right? They want to be really high on the pressure. And if they get really high on the pressure and you're up here, well, now water doesn't boil at 100 degrees anymore. You can get it hotter and hotter and hotter and give it more and more energy so that now it's not going to boil until it's all the way up here at whatever that temperature would be. So that's the idea of this pressure and temperature, and that's why you have your nuclear reactors are under pressure so that you can not get that vaporization or reach the boiling point. Just two little things. Critical point is it is the temperature at which you can no longer be a solid or a liquid. At that temperature, you'll always be whatever the substance is would always be a gas. And then the triple point is where all three phases of matter are present. So if you had water at 0.6 kilopascals and 0.1 degrees Celsius, you could have something where there is solid ice, liquid water, and water vapor, all three states of matter would be present at that triple point. That's it. You can move on to the worksheet.